Okay, let's get started. So, I posted the homework number 4 on the Blackboard. Okay, so actually the homework number 4 covers this what is this this chapter. It's a memory hierarchy chapter. Okay, so as I mentioned, this chapter is also important. So right, and then actually the final exam obviously will cover this memory hierarchy part, right? So try to answer the homework questions by yourself. So it will be very helpful. And then so the 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 final exam questions can be similar to the questions in the homework, right? And then I believe so if so so if you try to answer the homework questions, then you can understand what we are learning, right? So even though, and as you know, the homework questions covers the virtual memory part, but we did not learn about the virtual memory yet. But so after this chapter, we will take the final exam. So that's why I posted the homework early. Okay. So so we are learning about the cache, right? So what is a cache? What is a cache? So cache is a temporary memory space, right? It's a temporary memory space. And then, so why do we use cache? Because we want to access the frequently used data quickly, okay? So we learned about the memory system, and then we learned that some memory devices are very slow, right? So which means that when you access this memory, then it will take a very long time, right? So when you learned about the process architecture, though we did not consider about the performance of memory systems, right? So we just assume that it will take only one cycle to access the memory, right? But actually it's not true, right? So and then, so we also learned that, so actually, so these memories, like instruction memory and then data memory, are actually level on cache, right? So, and then, so which means that actually when we consider the performance of this architecture, the processor architecture, then we also need to consider cache misses, okay? So which means that the requested data can be found in the cache or not, okay? So we need to consider the performance. So we learned how to allocate data in the cache. So because the cache size is smaller than the size of the main memory, so we cannot store the entire data in the cache, okay? So we just store the part of data in the cache. So we learned how the data is stored. So which means that we need to decide where to store the cached data or located data in the cache, right? So we learned about the direct mapped cache. So which means that we use the part of address, the part of the data address as the an index of cache, right? So this is the direct mapped cache. So, okay, and then, okay. So let's learn about some cache miss scenarios. Okay, so as I mentioned, we did not consider about the performance of memory systems, right? So we just assume the cache is always hit, okay? Also, okay, so which means that, so in a five-stage pipeline architecture, so there are two memories, like instruction memory and data memory, right? But as I mentioned, these memories are actually level on cache, okay? So which means that we can just encounter cache hit or cache miss cases. So on cache hit, so if the cache is hit, then we can find the request data in the cache, right? So which means we assume the level 1 cache is very fast, right? So CPU proceeds normally. So which means that the cache access time is lower than the clock period. So we just assume that we can read the requested instructions from instruction memory within one clock cycle. Also, we can read the requested data in data memory within one cycle. Okay, so this is the cache hit case. So we do not consider about the performance degradation for the cache hit case, right? But the cache miss, then what will happen? So if the processor encounters cache miss case, then which means the request data is not found in the cache. Then the processor needs to access the lower level cache, but it will take longer time. So, which means, so for example, so in the instruction fetch stage, so in the instruction fetch stage, a processor accesses instruction memory to fetch an instruction. But we can also encounter a cache miss case, right? Because the instruction memory is also level 1 cache. Then what will happen? We try to fetch instruction, but instruction is not found, right? But it will take longer time. Then an instruction is stored in the instruction fetch stage, right? Then what will happen? Because the current instruction is stored in the instruction fetch stage, and obviously the next instructions cannot be executed in the instruction fetch stage, right? So current instruction is stored. Is current instruction stays in the instruction fetch stage for many cycles, right? And then, so it works like this. So the instruction cache miss, then the cache miss is encountered, then a processor needs to access the lower level cache, such as the L2 cache. Then the requested cache block will be allocated to this instruction cache, the L1 I cache. Okay. Then after the requested block is allocated in the L1 instruction cache, then a processor can access the requested instruction again, right? So in this case, this is the cache hit case, right? Because the request block is allocated. So then this instruction can be propagated to the next stage, and then the next instruction can be in the instruction fetch stage. And how about the data cache miss? So we can encounter data cache miss for load or store instructions, right? So what will happen? So this is the five architecture. So we can encounter a cache miss in the memory stage, right, by load instruction, like for example, load instruction. Then, so load instruction try to fetch a certain data from the memory, this data memory. And so actually this is the level 1 data cache, okay? L1D cache, right? But it's a cache miss. So then a processor try to access the request data from the row level cache, like the L2 cache, right? But it will take longer time. So the processor will consume more cycles. Then what will happen? The load instruction cannot be executed in the memory stage. The load instruction needs to wait until the request data is fetched from the low level cache or memory. Then what will happen? The load instruction stays in the memory stage. Then there can be some other instructions like add, sub, or branch, so some other instructions. And then because the load instruction stays in the memory stage, these instructions, the following instructions cannot be also propagated to this memory stage, right? Because it's stuck. It's stuck. The load instruction is stuck in the memory stage. So following instructions cannot be propagated. So this is the cache miss scenario. And then when the request data, the requested cache block is allocated in the level 1 data cache, then load instruction can fetch data from this level 1 data cache, then it can be propagated to the write back stage. Then the following instructions can be also propagated. Okay, so we can understand the cache miss scenario in a 5-stage pipeline architecture like this. So if the cache miss is uncounted, then what will happen? The clock cycles will be wasted. Then how much? How many clock cycles are wasted? So if the clock cycles are wasted for accessing low-level cache or memory, then these clock cycles are called the miss penalty. So miss penalty represents the additional clock cycles for processing cache misses, right? So we just assume that when the cache hit, then the clock cycles are not wasted, right? It will just consume one cycle. And then this is the normal case in the 5-stage pipeline architecture. So we assume that in the 5-stage pipeline architecture, each stage will take one cycle, right? So the clock cycles will not be wasted. But for the miss cases, then because of miss penalty, so this is the additional clock cycles for handling cache misses. So this amount of clock cycles will be wasted by these cache misses. Okay, so you can understand the cache misses like this. Okay, so then later we will calculate how many cycles can be wasted by cache misses. Okay, but so we will also learn about how the cache behavior for write operation. So until now, so we just assume that the load instruction, so or the instruction fetch, so which means that we just assume the data is read from the cache. But for the data cache, or so level 1 data cache, then we can also consider store instruction. So what is the store instruction? The data in memory is updated. Then how about the data in level 1 data cache? So when the store instruction is executed, right? Store instruction is executed, then it will update the data in the cache, right? But I mentioned that the cache is the temporary space, right? And then so the instruction needs to modify or update main memory. So this is the, the definition of store instruction. Then, so which means if the store instruction is executed, then this store instruction needs to update the memory, right? So main memory. But now, so we learned about the cache, right? So which means that we can just assume the scenario that which means, oh, this store instruction is executed, then I'll try to access the cache, but the cache block is found, the requested block is found in the cache. Then what should we do? So we can consider the possible two scenarios. So this is the write hit case. So this is called the write hit. Okay, write hit means that, oh, we want to try to update data, but this data is found in the cache, right? And then I mentioned that the cache block size is actually large. Okay, so which means the store instruction is executed. So we can just update the part of the data, part of cache block like this. But you can think like, oh, what is the protocol, or what is the definition of store instruction? The definition of store instruction is updating main memory, right? Then, so what should we do? So actually, so this is the write hit case. Oh, data is found in the cache. So we just update this data. Then how about the main memory? So there are two possible scenarios. It's a write through scenario. So it's called the write through policy. Okay, so write policy represents that if the store instruction is executed and then the cache block is found, the data is found in the cache, then the cache block is updated, and then immediately the main memory is also updated. So the write through policy actually it's the same to so actually it reflects the definition of store instruction, right? It just implements the definition of store instruction. The cache is updated and immediately the main memory is also updated. So this is the write through policy. Okay. Then what's the problem? The problem is, oh, cache is fast, right? So we can, the store instruction can update the cache within one cycle, but main memory is so slow. So in order to implement the write through cache, then when the store instruction is executed, then the main memory also needs to be updated immediately. And then it will take longer, okay? So this is some computation. So the base CPI, the clock for instruction is 1, and then 10% of instructions are store instruction. And then write to memory will take 100 cycles. Then what is the effective CPI? So which means that the additional 100 cycles will be taken if the store instruction is executed, but the percentage of store instruction is 10%. The effective CPI, so 1 plus 0.1 multiplied 100, so it's 11. So what does that mean? So for this processor, in order to execute so for executing one cycle, this processor will take us the one instruction for executing one instruction. This processor will take us 11 cycles. It's a huge performance degradation, right? So we just assume the processor takes one cycle per instruction, right? This is the baseline, the ideal performance. But for this assumption, the processor will take 11 cycle per instruction. So it's a huge performance degradation. So in order to avoid this performance drop, that we can use the buffer. Okay, so the right buffer means that so we can add the buffer here. Okay, because the main memory is so slow. Okay, it's so slow. So in this case, the write request can be buffered in this write buffer, right? Then the request is buffered here. Then the, the store instruction is done. So in this case, the updates to main memory will be reflected later, right? But the request is immediately given to this write buffer. Then the update will be slow, will be done later, but the write through policy can be implemented. Also, we can avoid the huge performance drop by write through policy. So in this implementation, that we can just find some in the inconsistency. So which means that for certain time, the data in cache is different from the data in main memory. Okay. So, and then another policy is write back. Okay. So write back means that, so this is the cache, this is memory, and then it's a write hit case. So store instruction is executed, then the part of cache block will be updated. But we can assume that, oh, when a processor execute the next instructions, then processor can just access this cache block, right? This is the updated cache block. And then if the updated cache block is in the updated data is in the cache, then some other instruction like load instruction will access this updated data in the cache, right? So this processor can always access the updated data in the cache. So what does that mean? Actually, we don't need to update the main memory immediately, right? Because so the processor will firstly access the cache, right? Then, oh, this is updated block, updated data. So we can read this updated value. So we don't need to update main memory immediately. So the write back policy, then if the store instruction is executed and then so the write hit case, then only the cache block is updated. Then when this memory is updated, so this is the latest data, right? And then this is the old data or stale data. So stale. Okay. So actually, so this data needs to be updated by this new data, the latest data, right? When? So I mentioned that if data exists in the cache, there is no problem. It's not no. So, but when is the when this block is evicted from the cache, then this is the problem, right? So in the write back policy, when updated cache block is evicted from the cache, then this cache block is updated to the main memory. Okay? In the write-through policy, if the cache is updated, then the main memory is updated immediately. But in the write-back policy, the cache is updated only. And then if this updated block is evicted from the cache, then the main memory is updated. So then there is no problem, right? So because, and then if the cache miss case, then the processor will also access this main memory, and then this new data will be allocated to cache. So the most CPU employs write-back policy. Okay, so and then in order to implement the write-back policy, then we need to check the cache block is updated or not. Okay, if the cache block is updated, and then when this block is evicted, then the main memory needs to be updated. So if not, then this block is just removed from the cache, right? So we need to check if the corresponding cache block is updated or not. So we require one more flag, okay? And then this flag is called the dirty bit. Okay, so if the dirty bit is 1, which means that this cache block is updated. If the dirty bit is 0, then the corresponding cache block is not updated. Okay, so when the dirty bit is 1, then the cache block is evicted, then the main memory is also updated. So this is the write-back policy. And then also we need to consider the write miss case. So write hit means that, the store instruction is executed, then we want to write some data to the cache, but this data is found in the cache. Write miss means that, this is the cache, then store instruction is executed or try to write data to the cache, but this data is not found in the cache, right? This is the write miss case. Then what should we do? So there are two possible policies. So allocate on miss. So allocate on miss means that, this is the write miss. Okay, so write miss. Then the cache block is allocated to the cache, okay, from the low level cache or the main memory. Okay, so fetched from the low level cache or main memory. Then it's allocated first, and then this cache block is updated. This is the allocate on miss policy. Okay, so for the write miss, then firstly we fetch the cache block, and then the cache block is updated. The write around, then this block is not updated. It is because it's just data update. So it passed the cache, and then it just update the main memory or the low level cache directly. Okay, so don't fetch the block. So there are two cases, but for the most case, so we can expect that if we just update a certain value, then we will usually we can use this value in the near future, right? We can just write the code like this. If we just update some values, then the updated values will be used in the near future, right? Because of temporal locality. So usually for the write back cache, we just use the allocate on miss. Okay. So which means for the write miss case, then the entire cache block is allocated to the cache first, then this block is updated. Okay, this is the write miss case. Okay, so you can read the, you can see the example of a cache. Okay, and then so we can just consider some miss penalty. Okay, so actually, so this in this example, so we use the DRAM, and then so we assume that the DRAM we can read the access latency for the DRAM is 15 cycle. Okay, and then we assume that we can read the DRAM for 1 word per access. Okay, 1 word per access. So then we can calculate the right some cache miss penalty for this case. So this is the some configuration, the 1 bus cycle for address transfer. So which means that it will take 1 cycle for transferring address, the requested to the RAM, and then it will take 15 bus cycles for every access. So every access to the RAM, and then also 1 bus cycle per data transfer. So you can understand like this. So this is the cache, and then this is the DRAM. Okay, and then there is a bus. So bus is the some uh, it's the interconnection network or some data communication channel between some between 2 components, right? So actually, the in order to transfer address or data, it will take time. It will take time in the bus, right? It's called the bus. Okay. So this is the configuration. And then in this example, the block size of cache is 4 words, and then actually the DRAM is 1 word wide. Then what is the miss penalty? So the cache miss is encountered in this cache, then the request is given to the DRAM, okay, in this configuration, okay, the DRAM, and then we need to access the DRAM in order to fetch data from the DRAM, and then the data is transferred to the cache. So firstly, the address needs to be given to the DRAM, so it will take 1 cycle, right? And then in order to read 4 words, but because for this one miss transaction, then we need to fetch 4 word data block, the 4 words data. So in order to read this word from the RAM, then it will take 15 cycles per word. So it will take 60 cycles. And then, so in order to transfer each word to the cache, then it will take 1 cycle. So the totally, it will take 4 cycles. So this is the total cycles for transferring data to cache. Okay, so 64 bus cycles. Okay, so this is the miss penalty. So we can calculate the miss penalty like this. But actually, in a real system, so actually this miss penalty is influenced by many factors. Okay, so for example, so actually we can implement the system using some many buffers and then queues. Okay, like queue. So actually the data fetch latency is highly influenced by some buffer delay or queuing delay. It's called the queuing delay in a system. Okay. But we can just estimate the miss penalty like this. So, but this is very simple, and then so it's a theoretical calculation. Okay. Okay. So then let's see how to measure the cache performance and then how to improve the cache performance. Okay. So until the chapter 4 in the process architecture, we just consider the performance of CPU, right? So instruction is fetched from the instruction memory, but it will take only one cycle. And then also the the load instruction will fetch data from the data memory, but it will take only one cycle. So when we consider the CPU performance, we just consider the hazard, right? Hazards. How to handle hazard in a CPU architecture. But now, so we are learning about the memory system, right? And which means that the data is transferred from the memory to CPU. So which means we also need to consider the performance of memory system. Okay, it's a performance of memory. Then how can we figure out, how can we uh, calculate the performance impacts from memory system. Okay, so until the chapter 4, okay, process architecture, so we assume every memory is ideal, right? So we do not consider about the additional cycles by memory systems, right? So we just assume the memory is fast, so it will take only one cycle. So, but we are learning about the real memory system, so which means the memory is slow. So the, the cycles will be wasted, okay? So we need to consider this wasted cycle. So when we consider the performance of a memory system, then we can just add these wasted cycles to the performance of CPU. So we can understand the performance impacts by memory system like this, right? So firstly, we assume the memory is ideal, so it's perfect. So we do not consider about the performance of a memory system. And then we just calculate the performance of CPU, right? The performance CPU with ideal memory. And then we can add the wasted cycles by memory system, right? So then how can we calculate the wasted cycles? So it's a memory store cycles. So this is just a very simple assumption, right? So in a program, and then among our entire instructions, we can count the number of memory accesses. So the memory is accessed for instruction fetch, right? So for instruction fetch, a processor needs to access memory, the instruction memory or instruction cache. Also, load or store instruction. When the load or store instruction is executed, then the data memory is accessed, right? But for the hit case, we don't need to consider the wasted cycles. So we need to consider the wasted cycles for miss cases. So we can calculate so this is the number of memory accesses per program, then multiplied by miss rate, and then also multiplied by miss penalty. The miss penalty is the additional cycles for handling cache misses. Okay, so this is the additional cycles by cache misses. Okay, so we can compute this cycle like the number of instructions per program and then number of misses per instruction and then multiplied by miss penalty. So this is the additional cycles. Okay. And let's see the example. So it's a cache performance example. So this is the some assumption. The instruction cache miss rate is 2%, and then data cache miss rate is 4%, and the miss penalty is 100 cycles. And then base CPI is 2. So which means that this is the ideal cache. So with the ideal cache, then the base CPI is 2. Okay. Then load and store instructions occupy 36% of instructions. So, and then we can calculate the additional cycles. So wasted cycles by cache miss. For the instruction cache, every instruction needs to access instruction cache, right? So actually the every instruction is a 1, okay? And then the cache miss rate is 2%, is a 0.02, it's a miss rate. And then what is the miss penalty? The miss penalty is 100. So if we calculate this one, then it's 2. So this is the additional cycles by instruction cache misses, right? How about the data cache? For the data cache, only the load instruction and store instruction will access the data cache. That's why we need to use the percentage of the load and store instructions. So 0.36 multiplies the miss rate is 4%, 0.04, and then miss rate, miss penalty, 100, 0.04, and then multiply 100. So this is the 1.44. So this is the additional cycles by data cache misses. So then what is the actual CPI? So ideal CPI 2 plus 2 plus 1.44. So actual CPI becomes the 5.44. So if we just compare the performance of ideal CPU and some actual CPU, the CPU with some actual not actual the memory system, right? Then the ideal CPU is 2.72 times faster than the more realistic CPU that considers the cache misses. Okay, so we can calculate the performance impacts by the memory system like this. Okay, so then you can observe that. So we can find that the cache miss rate is very low, just 2%, and then just 4%, right? It's very low. And then actually 100 cycle, it's also actually low. So actually this miss penalty is very, and in order to calculate the real miss penalty, it's very complex, but actually the 100 cycle is low. But we can find that the performance is dramatically degraded because of this memory system. Okay, so that's why the memory system the performance of a memory system is critical. Okay, critical for the performance of entire computer system. Okay. Okay, so and then we can define some the performance metric of the cache or performance metric of the memory systems. So it's called the average memory access time, or called the average memory access time is called the AMAT. Okay, AMAT, AMAT. And then we can calculate the, so AMAT is the average memory access time. So which means that, oh, this is the cache. Okay, then the processor will access the cache. But we can consider the hit case. We need to consider the hit cases or miss cases, because for the cache hit, the processor can access data very quickly. And in the miss case, then it will take very long time. So AMAT is defined as the hit time plus miss rate multiplied by miss penalty. Okay. So what is hit time? Hit time means that, oh, cache, the CPU accesses a cache, then, oh, data is hit, then the cache can provide the request data. And then in the miss, for the miss cases, the miss penalty is added. So AMAT is defined like this, and but actually for the miss case, then also the CPU needs to access the cache. So hit time is common for the hit or miss cases, right? And then miss penalty just defines the additional cycles for miss, okay? And then based on this AMAT, based on this data, then we can calculate the average memory access time. So this is the example. The CPU with 1 nanosecond of clock, and then hit time is 1 cycle, and the miss penalty is 20 cycles, and miss rate is 5%. Then what is the AMAT? AMAT is, if we just calculate the average memory access time, then it's 2 nanoseconds. So which means it's 2 cycles per instruction. So what does that mean? If we do not consider the cache misses, then we just assume that, oh, this is the instruction cache, okay, L1 I cache, and then actually the access time is very low, so that we can access for the instruction fetch stage, then we just a processor consumes 1 cycle for instruction fetch stage, right? But if we consider the average memory access time of instruction cache, then for this information, the AMAT becomes the 2 nanosecond. So which means actually it's just the 2 cycles, because it's a clock cycle. And then we know the the pipeline architecture, the works with the clock signals, right? Synchronized with the clock signals. Okay, so 2 cycles. So what does that mean? For the instruction fetch stage, actually this, and on average, this pipeline architecture will consume 2 cycles, not 1 cycle, because of cache miss. It's a huge performance drop, right? And then we can also calculate the average memory access time like this. So hit time plus unit hit average. So you need to the memorize this AMAT. Okay, so it's the hit time plus miss rate multiplied miss penalty. So we learned how the cache misses influence the performance of the CPU or the computer system. Okay, so which means, oh, actually, the performance of a memory system is very critical. It's very critical to the performance of the computer system, right? Then how can we increase the performance? So then how can we, so in order to improve the performance, then we need to improve the cache performance, right? Then what is the cache performance? The which factor will decide the cache performance. So we need to consider which factors will decide the cache performance. So when we consider the cache performance, what is the important factor? So if you see the AMAT equation, then it's the hit time plus the miss rate multiplied by miss penalty. So actually, these factors, hit time, miss rate, miss penalty, will decide the performance of cache, right? So these factors are all important. But when we consider the cache organization or cache configuration, then we can also focus on the miss rate, right? So actually, hit time and miss penalty is determined by the characteristics of memory system, right? So which means, oh, if the memory is fast, then hit time is low. If memory is slow, hit time is high. And then the miss penalty, this miss penalty is also determined by the performance of low-level cache or main memory, right? If main memory is low, miss penalty will be increased. But how about the miss rate? Miss rate can be determined by cache configuration. Like what is the cache configuration? So cache size, right? If the cache is also cache size can also influence the hit time, so, but the miss rate is also influenced by the cache size, and then block size, cache block size, and then cache association. So actually, we learned about the cache size and then block size, but we do not learn about the cache associativity. So this is called associativity. So now, so we will learn about the associative cache. Okay. So, so when we learned about the cache, then firstly we learned about the direct mapped cache. So what does that mean? So we can use the part of address field as the index of cache, right? So this is the direct mapped cache. And then one student asked about this disadvantage of direct mapped cache. So it is because, so actually in the direct mapped cache, multiple memory blocks can be mapped to the same cache block, right? Then what's the problem? Oh, this is the variable A, and then this is the variable B, right? Then we want to access a program want to access the variables A and B. And unfortunately, the variable A and B can be mapped to the same cache block. What's the problem? Our application will frequently use the variables A and B, but because of cache mapping policy, this cache cannot contain A and B at the same time. This is the problem, right? So do you understand the situation, right? The different data can be mapped to the same cache block, but because of a mapping policy, even though the cache has the empty space, empty blocks, but A and B needs to be mapped to the same block. So this cache cannot include the A and B at the same time. So what does it mean? When the A is requested, then was missed in the cache, and then after that, A is allocated in the cache, and then after that, B is requested, then also it's also cache miss. Then B is also allocated, and then A is evicted, and then after that, the A is requested, then A needs to be allocated again, and then B is evicted. So this is the disadvantage of direct mapped cache. Then what can we so we can consider the possible solution, right? If we store data to any location, any entry of the cache, then we can avoid this problem, right? So what is the problem? What is the issues of direct mapped cache? The multiple data blocks needs to be same to the same cache block, mapped to the same cache block, but there's only one cache block here. So for this conflict case, then the cache performance can be degraded. The miss rate can be increased. And then, but another problem is that cache space is not used efficiently. Right. Even though the cache has empty spaces, empty blocks here, but because AB is just mapped the same block, so empty spaces is not used. Okay, this is the disadvantage of direct mapped cache. So if we can allocate the data to any blocks or any entries of cache, then we can avoid this problem, right? So this cache is called the fully associative cache. Okay, so we are learning about some different mapping policy, right? So fully associative means that the data can be allocated to any cache blocks. Okay, so cache index is not determined by addresses. So it is because we can store some blocks to any entries of the cache. So this cache is called the fully associative cache. Then, but you can find that this is very good, right? So we can avoid this some mapping the performance degradation by mapping policy, but fully associative cache is expensive. Why? It is because, so I mentioned that when you learned about the cache, in order to identify data in the cache, we need to store address. Okay, but we don't need to store entire address. So it is because we can use the part of address as the index of cache. And then I mentioned that this is the tag. Okay. So the fully associative cache, the target index. Target index is not determined by the address of data. So what does that mean? We need to store entire address as the tag. Also, in the direct mapped cache, if the index is determined by address, then we can just compare the tag, the stored tag with the address of the request. Right. For this operation, we just require only one comparison. How about the fully associative cache? So we don't know. So if we just check the address, so we don't know the target index because the target index is not determined by address. So what does that mean? In order to check the tag match, which means we need to check entire blocks. For the direct mapped cache, we can just check the tag, one cache block and the address of request. How about the fully associative cache? So we don't know, we cannot figure out the target index of the cache, right? So which means actually we need to compare entire blocks, the tags in the entire blocks. Do you understand? So comparator. So we require the number of comparators, which is equivalent to the number of blocks. So it's expensive. So in order to, so the cost is high, even though we can improve the performance of a cache, but the cost is high. So with the alternative approach, that we can organize the cache as the n-way set associative cache. So n-way set associative cache means that, so what is the problem of direct mapped cache? So actually for this one cache block is mapped to the multiple data, multiple memory blocks, right? Then if this target block has multiple blocks, then we can avoid the, actually we can reduce these conflict cases, right? So the problem of direct mapped cache means that, so this cache block has the only one block, okay? So which means if the multiple memory blocks are mapped, then we can just store the only one block. We can avoid this case because if we just make multiple blocks mapped to the multiple memory blocks, this is the set associative cache idea. Okay, so in this case, if the two data is mapped to the same block, then we can store A here and then we can store B here. So what does it mean? Actually, we can define some different cache configuration. So this is called the set. Okay, so in a single cache set, there are multiple blocks, and then this set index is determined by the part of address. So this is the set associative cache. So unlike the direct mapped cache, so direct mapped cache is equivalent to the one-way set associative cache, which means that one cache set includes the one block, but n-way set associative cache represent there are n blocks per set. Okay, this is the n-way set associative cache. So unlike the fully associative cache, then if the target set is determined by address, then we can just compare the blocks in the target set. So what is the benefit? We can reduce the number of comparison. Because if the set is determined by address, then we can just compare the n blocks. Okay, it's the NA set associative cache. Okay, so let's see the example. So this example shows that a cache has 8 blocks. Okay, right? So the same number of blocks are allocated to the cache. Okay, in the direct mapped cache, a single block is mapped to the multiple memory blocks. Okay, so you can find that you can think that this is the set. Okay, but in a single set there is only one block. Okay, so if the index is detected, index is determined from address, then we can just compare the one tag. This is the direct mapped cache. So this is the example of two-way set associative cache. So it means, one set, there are 2 blocks. Okay. So when the set index is determined from address, so we can compare 2 blocks. Fully associative cache. So there is no concept of set, okay, because the data is stored any block, any location of a cache. So in this case, we need to compare every block. Okay, this is the fully associative cache. So let's see the example. Okay, so we will compare the. Let us assume that the cache includes the 4 blocks. Okay, and then we will compare direct mapped and then two-way set associative and then fully associative cache. And then this is the block access sequence, the 0, 8, 0, 6, 8. So the block address is 0, then cache index is 0. So because it's a 2 block, okay, so which means among this block address, so this is the block address, then the lower 2 bit will be as the index of cache, right? So cache index is 0 for the 0. Then initially the cache is empty, so it's miss, right? It's a miss. And then the block address is 8. Then cache index is also 0. What's the problem? Oh, in the direct mapped cache, because the cache index is 0, then this data needs to be allocated, right, to this cache block. But this cache block includes the different data. So this is miss. So it's missed, and then it will allocate the new data block. Okay. And then 0 also is missed because it's 0. And then if the cache address, the block address is 6, the block index becomes the 2, then it's also miss. Okay, right? But it's allocated to the different cache block. 8 also miss because it is 8, then it needs to check the cache index 0, but the cache index 0 includes the memory block 0. So it's also missed. So for this block access sequence, then what is the result of cache? All misses. Okay. Then how about the two-way set associative cache? Okay. So with the, so this is the total number of blocks. So, and then it's a two-way set associative cache. So which means that one set includes the two blocks per set, right? Then how many sets are there in the cache? Because each set includes the two blocks, there are two sets, right? Obviously, this is the total number of cache blocks. So you can find the set number 0 and then set number 1. Then how can we calculate the set index? Because there are only two sets, we can figure out set index is the pin number 0 of block address, right? Because this is there are only two sets. So you can find that this is cache index, but you can find that this is the set index. Okay, set index. So block address is 0, 0, then it's empty. So it's a miss. 8, then 8 will be allocated different block in a same set because the set index is the same. So what is different? In the direct map to cache, when the block address 8 is accessed, then this memory block is evicted from the cache. But in the set associative cache, you can find that memory block 0 exists in the cache. It is because in the same cache set, there are two blocks. So new blocks can be allocated to the new empty block, right? Then 0, because the memory block 0 exists in the cache, result is hit. Okay. And then 6, the cache index is 0, right? Because we need to use the LSB, pin number 0 of the address as this set index. So it's a miss. So in this case, we need to select which block will be evicted. Okay. So because in the 6, this is the new access to the cache, but there is no empty space, empty block in the target set, right? So this is set index is 0. Then we need to determine which block will be evicted. So in this case, mem8 is evicted because the mem0 is accessed recently. Okay, so we will also learn about the cache replacement policy later. So the memory 6 is allocated and then it's a miss. And then the next access is 8. Then memory 8 is checked in the cache, but the 8 is evicted, so it's a miss. In the two-way set associated cache, but we can observe one hit. Okay, it's different. How about the fully associative cache? The fully associative cache, the set index is not determined by address, but you can think that there is no concept of set. Memory block can be allocated to any location of a cache. So it's a 0, miss, 8, miss, but it's a store allocated 0, then it's a hit. 6, it's a newly allocated to the empty space, empty block. Then 8, it's a hit. So you can find that in the fully associative cache, then there are 2 hits. So based on the set associativity, then we can find that we can reduce the cache miss rate. Okay. So also this is the the very important part of the cache. Okay. So, okay. So I will stop here. And then any question? Okay. See you in the next class. 감사합니다.